In this video, we will go over how to do a Bode plot for a second order system. We have data collected from a second order system. We have the input. So we input like a sine wave, and the output of the system. We record the changes in amplitude and the change in phase. Okay, so our sine wave looks like this, the input sine wave, and the output is going to be the same frequency at steady state, but the amplitude might be a bit less or a bit more. Okay, so and the phase would be also shifted by a bit. Okay, and we measured both of this experimentally. So to get the phase, we measured features and the time difference between two features. Okay, so this is our delta t. Okay, this is the delta t that we recorded. Okay, and the new amplitude is what we recorded as a out. Okay, a in we kept it the same. This is pi over 6. Yeah, pi over 6. Okay, so you can see the amplitude is changing over time, and if we look at it, you can see the amplitude gets higher at certain frequencies. Okay, and it's lower in the beginning. I mean, it's kind of stable in the beginning, and then it goes lower towards the end at higher frequencies. Okay, this is expected of a second order system. Okay, so now let's calculate the things required to make a Bode plot from the data given. So all we care about is the magnitude in dB and the phase in degrees. Okay, to estimate the magnitude, you need to find the ratio between the output and the input. Okay, so let me name all these range so that I can reference them in the formulas easily. So this is going to be my A in. This is going to be omega. This is A out. And this would be delta t. Okay, so the magnitude is just m, which is the output, the ratio of the output amplitude over the input amplitude. So this is A out divided by A in. Okay, and in dB, you're gonna just do 20 log of base 10 of the magnitude. So 20 times log 10 of the magnitude. So let me call this the magnitude m, and this would be 20 times log 10 of the magnitude. And that's our magnitude in dB. For the phase, here is the equation that you need to use to estimate the phase given the delta t. Okay, so this is going to be equal to minus 180 divided by pi times omega times delta t. Okay, now remember delta t is in milliseconds, so you need to divide this by 1,000 to bring it back to seconds. Okay, so here you can see it starts off at close to -0 and then increases all the way up to -180. And this is what you expected from a second order system. And now let's make the plot. You can then insert a plot. Okay, so this is our magnitude plot. So let me just change the layout to something like that. Okay, so this would be our magnitude in dB, and this is our frequency in radians per second. Okay, now this is not exactly a proper Bode plot because you should have the x-axis in a log scale. So double click on your x-axis, and you can change the property here to make it logarithmic scale. Okay, better. And this is the data that we collected. We're gonna also show the model on top of this. So let's name this as data. So you can select your data, and up in the formula here, the first value is the name of the data. So you can use quotation marks and just say data. Let's do the same thing for the phase. So I'm just going to make a copy of this. Okay. So now let's try to see how to get the model and show the model on top of this. Okay. So this would be the standard form of the second order system. There are two parameters that you have to know to make the model. You need to know the natural frequency of the system, omega n, and the damping ratio, zeta. Okay. In order to make this, so this is the transfer function of the system. In order to draw the Bode plots, you have to have this as a function of frequency, omega. So you can change s to j omega, and then you have this one. Okay, and so j omega, so once you plug in j omega as s, s as j omega, this term you square it, the j becomes j square becomes -1, and that's how you get this negative over here. Okay, so now we have the real part here and the imaginary part over here. To get the magnitude, it's the magnitude of the numerator divided by the magnitude of the denominator, and the magnitude of a complex number is square root of the real part squared plus the imaginary part squared. Okay, remember that it's just the part, so you shouldn't put the j over here. And then finally, to get the phase is calculated as the phase of the numerator minus the phase of the denominator. So the first part is 0, it's a constant, and the phase of a complex number is calculated as tan inverse of the imaginary part divided by the real part. Okay, so we end up with this equation here, the imaginary part and the real part. Okay, so let's do that here. So the magnitude, so first we need to have omega n and zeta. Okay, so we need to estimate omega n and zeta. Okay, and we need to estimate this from the graph. Okay, so from the graph, you might try to go for this peak over here. This is the resonance peak. Usually it might be close to the natural frequency given that zeta is very low. Okay, but in this case I would say there is quite a bit of damping, so you don't want to estimate it from this value. This value is around 48. It might be close, but this might not be the right value. The next best way to estimate it is by looking at your phase and seeing where is the inflection point. Inflection point is when the phase changes from 0, it crosses the minus 90 degree mark. Okay, like halfway between 0 and minus 180. So it's a bit hard to see from the graph. You can actually look at the data and estimate this. So your phase changes crosses the minus 90 mark around this value. So I would say 50. So let's assume your omega n is 50 radians per second. And zeta, now to find zeta, you can actually go back to the magnitude equation. And if you were to find the magnitude at, omega n, what would you find? So if you go to this equation, this becomes omega n and omega n. So you cancel to become 1. This cancels to become 1. And then 1 minus 1, this also entirely goes to 0. So what you end up with is, so square root of square, so that also disappears. So you have 1 over 2 zeta. Okay, so you can easily estimate zeta as being equal to 1 divided by 2 times the magnitude at omega n. Okay, so it's a very simple and straightforward equation. So we can find it, we just have to know what is the magnitude at omega n. So since we estimated omega n to be 50, you can go back to this graph and check at 50 what is your magnitude. So the magnitude would be this one. And this time the magnitude is not in dB, it's the linear scale. So be careful. So this is our magnitude in the linear scale. And at 50, we are at 1.47. So you just have to type it in here. Equal to 1 divided by 2 times. Okay, so it's so we have a bit of damping here. Okay, so let's plug that in now. So now we have zeta and omega n. So I'm gonna do the naming again. So this is omega n, and this is zeta. Okay, so I have omega n and zeta. So now my magnitude is calculated as this ratio here. That's our magnitude. It should be 1 in the beginning, and then it should start dropping to 0 towards the end. Okay, and in dB is going to be equal to, so this is our magnitude of the model, m underscore m, and this is dB, so it's equal to 20 times log 10 of magnitude of the model. Okay, and finally the degree, the phase, you can calculate it from this equation. This is our tan inverse, so in Excel it's a tan. Now there are two options, a tan and a tan 2. A tan is restricted to only two quadrants, so it goes from minus pi over 2 to pi over 2. So you want to stick to a tan 2 so that the phase doesn't jump when you plot it. Okay, so let's go for a tan 2. And in the a tan 2, you have to specify what is the x and the y number. So x is our real number and y is the imaginary number. So in our case, the real number is this one, 1 minus omega over omega n squared. Let's type that here. And I think that's it. Yeah. Okay. So yes, it should. So this one is calculated in radians, so, but we want it in degrees. So just multiply the final output by 180 and divide by pi. So you should see it starts at 0, crosses 90, and then goes to like closer, it gets closer to 180. I think we forgot a negative here. So there's a negative sign over here. Yeah. Okay. You can also review all your formulas at once. You just have to click on formula on the top and click on show formula. And this way you can verify if all the calculation is done correctly or not. Okay. These are long formulas. This is how we calculated the magnitude and the phase. Okay, so this is an advantage of writing using name ranges, so the formulas make more sense. Okay, so let's now plot the model on top of the data that we have. One trick I used to do this is just make copies of your plots. And you can just move this into the model. And then you can take the data, cut it, and then go back here and paste it. Okay, so now we have the model as well added here. You can do the same for the other one. Copy the plot, click somewhere else, paste it, just move it to the new place. Then you can cut it from here and paste it here. Okay, and now we have the data and we have the other one. So the other one is the orange one. Wait, so the data is the orange one. The blue one is the model. So let's click on the model and name it model. Okay, and then you might want to change the chart type. So if you go to chart design, change chart type, you want the model to be a line. So we can do a smooth line. Okay, hope this was helpful. And thank you.